Have you ever asked an AI a question about something that happened, like, yesterday, and wondered how it could possibly know? I mean, these models were trained months ago, right? Well, it's not magic. It's an incredible technique that basically gives the AI an external brain. So today, let's pull back the curtain and take a look at the fascinating architecture that's making it all happen.
Here's what we're going to cover. First, we'll talk about this idea of an external brain. Then we'll dive into the art of prepping all that knowledge, a process called chunking. After that, we'll explore the special library where it all gets stored, witness a showdown between the top databases, connect all the dots in the full RAG pipeline, and finally, wrap up with a winning strategy you can use for your own projects. All right, let's kick things off with the big idea that makes this whole thing possible. It's called Retrieval Augmented Generation, or as everyone calls it, RAG.
So this is the fundamental problem, right? Training a huge language model costs a fortune and takes forever. You can't just retrain it every single day to keep up with the news. So how do you give it access to that constant fire hose of new information without basically starting over from scratch every time?
Well, the answer is RAG. You can think of it like this. You're not trying to cram more facts into the AI's head. Instead, you're giving it a library card to the entire world's up-to-date knowledge. So when you ask a question, it doesn't just rely on its old memory. It goes to the library, looks up the most relevant facts right now, and then uses that fresh info to give you a way smarter, way more accurate answer. It's a total game changer because it separates the AI's reasoning skill from its knowledge base.
But, before an AI can use this amazing library, someone has to organize the books. And that brings us to a really critical first step in the process, called chunking. Honestly, this part lays the foundation for everything that follows. So the moment you start chunking, you're faced with this classic trade-off. If you slice your documents into tiny little pieces, you get super high precision. It's really easy to find an exact match for a question. But you lose all the surrounding context, right? On the flip side, if you use big, beefy chunks, you get all that rich context. But the specific answer you need might get buried in all the noise, diluting its relevance. It's a real balancing act. And you might be thinking, how much does this really matter? Well, it matters a lot. Research shows that just picking the wrong chunking strategy can create a performance gap of up to 9%. I mean, that is literally the difference between an AI that feels brilliant and one that's just frustratingly dumb. So, how do you get it right? Well, you've got a few tools in the toolbox. Recursive splitting is usually the smart default. It tries to find natural breaking points, like paragraphs. Then there's the simple, kind of brute force method, size-based splitting. Sentence-based is awesome for Q&A because it keeps whole ideas together. For things like PDFs, page-level chunking is often your best bet. And then you've got the really advanced option, semantic chunking, which actually understands topic shifts. But yeah, it's going to cost you more in computing power. And check this out. Here's some hard data from an NVIDIA benchmark. They found that for structured documents like PDFs, things like financial reports or academic papers, just treating each page as its own chunk was the most accurate and consistent strategy. It just works because it respects the way the author originally laid out the information. Okay, so we've sliced and diced our knowledge into these perfect bite-sized chunks. Now we need a place to put them. But not just any old folder, we need a special kind of library, one that organizes information by what it means. And this is where vector databases come in. A regular database is like a filing cabinet, organized alphabetically. You look for a specific keyword. A vector database is totally different. It's more like a mind map. It organizes info based on its meaning. Every single chunk of text gets turned into a long string of numbers. That's the vector. And chunks with similar meanings are placed close to each other in this giant multi-dimensional space. So you can search for a concept, an idea, not just a word. It's pretty wild. So who's doing this magic trick of turning words into numbers? You guessed it, the tech giants. These embedding models from places like Google, Meta, OpenAI, and Cohere are the engines that read our text chunks and translate them into those powerful vectors, ready to be filed away in our semantic library. All right, we have our chunks, and we have a way to organize them by meaning. Now we need to pick the librarian, the actual vector database that's going to run the show. And let me tell you, the market is hot right now, and each one has its own special talent. So here are the 5 heavy hitters. Pinecone is your simple, it just works option. It's fully managed, perfect for teams who don't want to mess with infrastructure. Qdrant is all about raw speed, built in Rest, and it's amazing at filtered searches. Milvus is the absolute beast for enterprise scale. We're talking billions of vectors. Weaviate is the champ of hybrid search, mixing old-school keywords with new-school vectors. And Chroma is a developer's best friend for spinning up a quick prototype. Okay, but how fast are they really? This unofficial benchmark gives us a pretty good snapshot. Now, you got to take any benchmark with a grain of salt, but look at this. Qdron is leading the pack at just 25 milliseconds for 95% of its queries. Milvus is right on its heels. Pinecone is a bit further back, but hey, we are still talking about searching millions of items in the blink of an eye. But here is a super important piece of wisdom, and it comes straight from the Qdrant team on Reddit. Speed isn't everything. You can always make a search go faster if you're willing to sacrifice accuracy. The real magic, the hard part, is being both fast and precise. It's all about finding that perfect balance. Okay, we've talked about chunking, embeddings, and databases. It's time to put it all together. Let's step back and look at the entire RAG pipeline from start to finish.
So this is the whole journey. Step 1, you gather up and clean your documents. 2, you run your chunking strategy. 3, an embedding model turns those chunks into vectors. 4, you load all those vectors into your database. Then, when a user asks a question, that question also gets turned into a vector. Finally, the system finds the most similar chunks from your library, hands them over to the large language model as context, and that model generates the final super-informed response. That's the whole shebang.
But there's a dirty little secret in the world of RAG systems. To get that pinpoint accuracy after that initial super fast search, the system often has to go back to slower storage to grab the original, full detail vectors to double-check and re-rank the top results. And this one step can be a huge bottleneck. We're talking it can eat up over 90% of the total query time. It's crazy. So given all these moving parts, these trade-offs and bottlenecks, how in the world do you actually make the right choices for your own AI project?
The most important thing to realize is that there's no single best answer. It all comes down to your specific use case. What kind of documents are you dealing with? What kinds of questions will your users be asking? How big is your data? And, critically, what's your budget for team time and for money? Answering these questions first will guide you to the right set of tools.
But look, if you want some practical, get-started-now advice, here it is. Don't over-engineer it from the beginning. Start with a solid, simple baseline. Use recursive character splitting. It's a fantastic default. Then, measure everything. Only if your metrics are telling you that you have a performance problem should you spend the time and money to explore those fancier, more complex strategies. Start simple, measure, and then iterate. And that really leaves us with one final, much bigger question. As we build these external brains for our AIs, using the entire library of human knowledge as the source material, we're doing more than just solving a tech problem. We are, in a very real way, deciding how to structure and organize all of human knowledge for an intelligence that isn't human. So, what's the ultimate strategy for that?